Python is everywhere nowadays. AI, LLMs, web development, and many more. But have you ever thought about what actually happens when you run a piece of Python code? If you are interested to know the answer, this video is for you. Step 1. Everything starts with the source code. You write your code in a file using an editor and then save it, usually with the .py format. Step 2. After you save your code into a file, you run it, typically by running the command or using a run button in your IDE. But what happens when you run this command? Before we step further, we should understand a key concept in the computer world: compilers. Computers mainly understand binary, meaning 0 and 1. But we write our code in human-friendly languages nowadays. In Python, the code we write is very close to human language. But how do computers understand this? Well, they don't. We need a program that takes this human-like code and converts it to the lower-level form that computers can understand. This program is called a language processor, or more commonly, a compiler. Simply, a compiler is a program that reads the program in one language, the source language, and translates it into an equivalent program in another language, the target language. We need a program that can understand our code and execute it. These programs are Python implementations. You should know that Python itself is just a specification of a language, and it can be implemented in different ways. We have several implementations of Python. The famous one and the default one is called CPython, because it's developed mainly in the C programming language. We have Jython, which runs Python on the JVM or Java Virtual Machine. We have IronPython, which runs on the .NET framework, and many more. Here we focus on the main one, CPython, but for simplicity I just refer to it as Python. CPython is an implementation of the Python language that contains many utilities. It can understand your code, or technically speaking, parse it, check if it complies with the strict grammar defined by the Python language, check for errors, optimize your code, and of course, execute it. Step 3. When the Python parser sees the source code file, it is just a stream of characters and it has no idea about its meaning. The first step is to tokenize this text. Tokenization means breaking a big text into smaller pieces that are meaningful for Python. For example, consider this Python program in which I defined a variable and assigned the value BMW to it. However, I did not put the enclosing quotation marks on purpose. When I try to tokenize this program in Python, it throws an error because it can't tokenize it, since it does not comply with Python grammar. But if you provide the program with valid grammar, it will tokenize it, even if the program has logical errors, for example, divide by 0. Tokenization is a great step, but it's not enough. Now we need a way to understand the tokens in groups, see how they are related to each other, what type of operations they perform, and so on. We do this by parsing the tokens into a tree data structure known as an abstract syntax tree, or AST. AST is about understanding the structure of a program. Consider this example. From the tokenizer's perspective, this code is totally fine. But when you parse it, you get a syntax error because of this part. Python expects to see an expression after the if statement, but instead, it finds two tokens that cannot form a valid expression. Have you ever seen syntax errors in your programs? This is where they get detected. AST is a high-level representation of the program without the necessity of containing the raw source code. Step 4. After you get the syntax tree, you need to create a symbol table. A symbol table is a data structure that keeps track of identifier or names in the program, like variables, function, classes, etc., and their attributes like their scope and type information. Here is an example of a symbol table created for the Fibonacci function. Step 5. Having the abstract syntax tree and symbol table in hand, the next step is to create a raw instruction sequence, which is roughly the instructions that will execute. Basically, your program is turned into a set of raw instructions. This set of instructions come from a known set, and each instruction represents a specific operation. These sequences of pseudo-instructions are similar to bytecode, but in some cases they are more abstract and are resolved later into actual instruction types. Step 6. Then this raw instruction sequence is converted to a directed graph known as a control flow graph or CFG, which models the flow of a program. A node of a CFG is not an individual bytecode instruction, but instead represents a sequence of bytecode instructions that always execute sequentially. Each node in a CFG is called a basic block and always executes from start to finish. CFGs are useful as an intermediate representation because they are a convenient data structure for optimizations. Step 7. Here we apply various peephole optimizations and create an optimized CFG. Step 8. Now that we optimized our CFG, it's time to convert it back into an instruction sequence. Step 9. Finally, the sequence of pseudo-instructions is converted into actual bytecode. This includes transforming pseudo-instructions into actual bytecode instructions, converting jump targets from logical labels to relative offsets, and constructing the exception table and location table. Step 10. The output of the previous step is a code object, which then will be executed by the Python virtual machine or Python VM, which is a stack-based virtual machine. And that's the full life cycle of running a Python program, from your human-readable source code to machine-executable instructions.